In our previous session, we discussed about theoretically what is binary search tree and what are the properties. So today we'll see like in C++ how we can implement a binary search tree. For this, we can include I was just for printing purpose. String namespace std. So let us create a class for that node basically. Tree node, which is so you know right like binary search tree we need data and its left node and right node. That's it, right? So what we can do is integer is the data. We'll try to fill the integer data only and tree node for left and left subtree basically and for right subtree. That's it. We'll try to write a one constructor which will take integer value and we'll try to fill with value and left and right will be with null pointers. Okay, so we are ready with we are ready now with the node tree node basically. So now let us create a class with bst. Okay, so this bst will have uh, uh, will have right one thing is we need a node basically, um, root node that we can treat as a root. Okay, so basically what we will do is in the private section we'll try to we'll see like what actually we can do in the void. We can try to implement no insert the operations like insert some value. Okay, so internally what we will do is we will try to root equal to insert root comma v. Okay, this is one thing we need to implement in public section, and also we discuss right we need to implement a delete as well. Delete value, these are the public sections actually we'll do. Delete root comma v. Okay, and the third one we what we need to do is we need to implement one more thing called searching also, right? Search an element integer value. Okay, root comma v. So we will implement these functions in the public section now, right? So yep, these are the this is what we are exposing. Mhm. Okay, so now what we will do is we'll try to implement in private section root node and we'll try to implement the insert functionality, right? Okay, Now what we will do is add insert node comma whatever the value we received basically, right? Integer value is v. So first thing what we need to do is while insertion time, we need to check if root node, whatever node we received is in null, right? You just need to return the new node, new tree node of value. Okay. Basically we are trying to return here, right? So that's it. So this is the base condition, right? This is what we want to find null, then we need to find. So second case, what we need to do is if the value whatever we received here, whatever value we are trying to insert, if that value is less than node's data, then where we need to insert? We need to travels for the left side, right? Node left equal to insert node left whatever value we received, this value. Okay. Otherwise, what we need to do is else if value whatever received that is greater than node data, in this case we need to insert right side, right equal to insert node right and whatever value we received. For example, if you found already in node that value is equal to node data is equal to whatever the we received value, then you simply return that node because that node already exists. This was simple in the recursive manner. Okay, very simple, right? Perfect. So now let us implement the delete method. Okay, so now what we need to do is we need to tree node star delete node comma integer value. So this is little tricky now. Delete basically suppose if base condition is if node basically a null pointer, you nothing to do because this particular node already deleted actually. Okay, cool. So there are some conditions basically, but first we'll try to use our base thing. So however we inserted similar fashion actually we'll check this value is less than node data. What we will do is we'll try to node left equal to remove that node left comma value. Basically once it base condition if you say, right, if the deletion means this will become null basically. Okay, similarly for other case, if uh, v is greater than node data, then try to delete from right side. Okay, right equal to equal to delete node right comma b. So these conditions are very cool, but yeah, these two things, two cases are is perfectly fine. So, but once you find that uh, you find that no, you found the element as it is, then what we need to know, if we need to check node left is null pointer. Cool. If it is a null pointer, then it's a null pointer. Then what we need to do is we need to check node right here. Okay, and delete node, whatever node we are trying to turn. Simply return temporary node. Okay. Okay. For example, if else if node right is equal to null pointer. In this case, actually left is not null, but right is null. This is the tricky thing. Then okay, equal to node. In this case, what we will do, we'll try to read the right node and delete node, and we need to return the temp node. So basically, if left node is null, then we'll try to return the right node and delete the current node. Similarly, for the right node is null pointer, then we'll try to return the left node. What if both are null? Basically, what if in the case like nodes left and right both are null? Then what we need to do is we need to find the I mean, uh, minimum node basically from its right side. Okay, get that data, and then you try to remove again no from right side. Let us see that how it works. So in the case like no the nodes whatever the trying to delete the node, that nodes left and right both are null. Then what we need to do is we need to find the minimum min node from the node right. Okay, why? Because in the right side actually anyway both are null, right? So uh, we need to go and check that right side actually. Okay, if that is the case, then what we need to do is we need to just try to get the node data as a temp data, and what we need to do is we need to try to see it's right. We need to delete basically delete node right comma. Here we need to delete the temp data because we already taken that one. Okay, so we need to find the minimum data. It's a very simple way we can find the minimum, right, in binary search. So we need to keep go left. Law leftmost thing is the actually is the minimum node, right? So what we need to do is we need to find the minimum node. Okay, so the function what we will do is we'll try to tree node star min node. We need to take the not start node. What we'll do is very simple way we'll finish it off this. We'll see that if node left is not equal to null pointer, then we just travel till left actually, or equal to node left. Okay, simple actually. We'll just try to keep moving left. Just return that one. So this will help us to know get this one actually. Okay. Mm, okay. So this is about the remove and mm, remove, sorry, delete and insertion. So now let us try to simply implement the search functionality. Okay. Search we discuss later. It will be returning boolean variable. So it will take tree node, comma. We will take the whatever value we want to search actually. Okay. So in this case, what we will do is if node is null pointer, basically we are not able to find the element whatever we need, we return the false. This is the best case. In other cases, like if so value equal to data, simple, right? Return true. Otherwise, what we can do is else if value is less than no data, then return search of. What we need to do is we need to go left actually, left node with value only. Okay. Otherwise, what we need to do is else we need to keep no search, return search of node right comma value. So this is how actually we need to search the function. It is very simple in the recursive manner. Okay. Okay. So this is how it will be. So okay. Now let us try to implement the other functionality, like how we can insert elements and we can search, delete everything. So we'll try to implement main function. So let me run this. Any compilation issues are there? Okay, there is no compilation as of now. So what we will try to do is we'll try to uh, insert actually the tree, like we will try to insert 50 first. Okay, and after that we'll try to insert 30. That should be coming back to here. Okay, and if I insert more than 50 value, maybe we'll insert 70. That will come right side. Next we will try to insert 20. That will come right, that is left node. Okay, and we will try to insert after that probably 40, so that it will come to check the 50 is less than this, then it will come 30. So greater than 30, then it will come here 40. Okay. After that, what we'll try to do, we'll try to insert 60. Okay, it will come to 60 to insert here. Okay, 60 is greater than 50, then it will come to 70 node. Then it will try to 70, 60 is less than 70, then it will come here and insert 60 as a left node. And finally, we'll try to insert 80, then it will come 80 here, greater than 50, so it will come here. 80 is greater than 70, then it will try to implement insert at a left of okay 70 80 left of 70. So this is what we'll try to insert basically now. Okay, okay, what we will do here is we'll try to create a class bst in simple terms. So so what we will do is bst dot insert, we'll insert like 50, that is what we discussed. Okay, 50 will be inserted as a root node, and then we'll try to insert 30. This will become left node of 50. bst dot, actually we are trying to insert this one. Let me minimize this. Okay, 30 we are already insert. Okay, okay, so we inserted 30. Then what we need to do, we need to insert 20 now. Insert no, not 20 also you can insert, that's not an issue. But I will prefer like let us insert more value, more than 50, so that you root node will have two nodes now, like left side 30 and right side 70. Now we'll try to insert 20, so that this value will be inserted at 30's left node. bst dot insert. Now I will try to insert 40, so that it will be no right node of 30. Okay, now what we will do is bst dot try to insert more than 50 and less than 70. I will insert 60. Insert, I will try to insert 80. Okay, in this case, actually, whatever we discussed in the tree is ready with these insertions. This is the binary search tree with the properties of binary search tree. Cool. So what we will do now is uh, we'll try to like print some search things. Okay. Uh, Assuming like let us search 40 is there or not. Okay. Okay, bst dot search. Okay, 40. Okay, we will try to do that actually by found 40, not found. Let's try to do this one. Let us run and see what happens. Okay, okay, bst search 40, 40 should be there, right? Yes. Okay, now Oh, okay. I try to do something here. Okay, let us see again. Let us compile this. Okay, what is wrong here? Search element. Okay. Hmm. BST dot search of element 40. Okay, see out found 40. Else see out 40 not found. Okay. Mm-hmm. BST we are insert nothing is printing. What is happening here? Oh, where I am? BST CPP only, right? Yeah. Main.cpp. Okay. Oh, let me debug what is happening here. Let me fix. Okay. Basically, what is happening here is well insertion time. Since we have not make the root node as a default null pointer, because of that it is crashing. So yeah, now it should work properly, because if you see, right, we have implemented we have taken one root node here, that because of that it is failing. But anyway, so now what we can do is we can try to run now. So in the main function, what we are trying to do here is we are trying to know try to find the 40 is available or not. So we'll try to do that. Example, now I built it. Now I will try to test that. Yes, we are able to see that 40 is available. Let us see similarly is a non-available thing. We can try to find 90, because 90 nowhere there in the picture. We'll see what will happen here. Okay. Okay. Build it. We'll try to run this. 90, 40 is found, 90 is not found, right? So what we will do next is we'll try to delete some number. Probably we can try to delete the 40, because we already tested that. Okay, what we will do is we'll try to bst dot delete 40, and we'll try to run the same thing. Let us see what happens. Okay, we'll again try to find the 40 from the bst. Member function, not bst control reaches end of. That is okay. Let us see now by running this. Yeah, if you see that we are not able to know, we are not found the 40 ones, we deleted that. That means like we try to validate the functionality of insertion, search, and delete, right? So